recording. Can you all see the screen okay? Okay. Folks at home, can you see the screen okay? Awesome. Before we get started, do we have any questions about this last homework maybe? Or ggplot in general?
I have a question.
Sure.
We will review our classmates'
Mhm.
work. Do we supposed to read the document or
Just a comment is plenty.
okay.
Unless there's like some reason to have like an in-depth description of a code change that you'd like to make, then just a comment is great. Awesome. Well, let's get started with week 3. I was feeling like very proud that I would have updated the slides ahead of when the day was today, until I realized there was a slight deprecated thing and I had to change it again. And then now the dates are the same. That's okay. We're going to be talking about manipulating and summarizing data today. I think it's just probably the first step we're going to be taking towards like cleaning data custodial work, which as social scientists is often how we spend our time. There's so much data cleaning that needs to be done in order for us to like answer the questions that we're interested in. And I think this is the first day where we really dive into that kind of work. So the theme for today's class is death to spreadsheets. We'd really like to just get away from Excel if we could. So today we'll be talking about dplyr. This is a package that does and are about any calculation you've tried to do in Excel, but more transparently, reproducibly, and safely. Don't be the next sad research assistant who makes headlines with an Excel error. You can read that article if you'd like. There is a more morbid version of this related to COVID that I do not like to keep as our pet example, but I'm sure we might have heard of that one as well. So let's talk about modifying data frames with dplyr. But first, we must talk about pipes. So we talked a little bit about pipes. I introduced them to you last week, and I know that some of you use them in your homework. Let's talk a little bit more about the nuances of them and why we would find them useful. So dplyr uses the magreader forward pipe operator, usually simply called a pipe. We write pipes by using the % greater than %. You can also type Control-Shift-M, or if you're on a Mac, Command-Shift-M. Pipes take the object on the left and apply it to the function on the right. This is all they do. An example would be object, pipe, function, argument equals y. This will be the same thing as function, object as this first argument here, comma, argument equals y. Okay. When we're describing what's happening in a chain of pipes, we read them aloud as and then. Okay. So here we can look at an example of a small chain. We'll need to load the libraries dplyr and gapminder in order to do this. And we'll take the gapminder data and then filter for values in the country column that are this equal to the word Canada, and then take the first 4 rows of the remaining data set. And our output will look like this. It'll be a table with 4 rows. That's just values where in their country column, their word is Canada. So this is probably the main benefit that we would want out of pipes, is that we can chain them together to do several manipulations in a row. Pipes can save us typing. They can make code more legible by allowing us to write things left to right and allowing chaining like above. So we use them kind of all the time when we're manipulating data frames and trying to change data into a specific format that we'd like. Let's talk about how we're going to use them. Pipes are clearer to read when you have each function on a separate line. I might have noted this last week that I tend to put things on separate lines for legibility. Sometimes in the slide, this is going to be slightly inconsistent because of the space constraints of the slide, but we typically want things to look like this. We want to take these data and then do the first thing with this value, and then do the next thing using that value, and we can keep chaining these almost forever. It used to be the case that you could only chain 50 Magrider pipes in a row. They since upped it, and I have not checked how much more you would need. I'd only ever hit the ceiling once back when it was 50. So I would say don't worry so much about the ceiling of how many times you can chain things together. An important thing to note here is that stuff to the left of the pipe is passed to the first argument of the function on the right. Other arguments go on the right in the function. So if you ever find yourself piping a function where data are not the first argument, use dot in the data argument instead. And this will target where the thing that's being piped is supposed to go. Okay, so for instance, if we wanted to take the Gapminder data and then run a linear regression of population by year, in order to get the Gapminder data to go into this function, we'd have to say data equals dot. Okay, and one follow-up question you might have is, how do I know when a function's first argument is data and not some other thing for which I would need to use the dot? If you go to the help in your let's see here. So we could say like help filter. Oh, this is important to know. When you select something for help that has like multiple packages with the same word for that function, it'll just give you a little drop down and tell you which one you can click on to check. So we're interested in the filter that's in the dplyr package. So we'll click on that one. But arguments that are listed in the help are in order that they come up. So our first argument for filter is data. Whereas if we did help LM or linear regression model function, the first argument here is formula. And that's why you can't just pipe things straight to it and have it recognize that this is the data and not the formula. Okay. And if you're wondering why it's dot, I would say don't worry about it so much. There's a really good reason for it that you can actually check, but that's kind of beyond the scope of this class. If you consider yourself like a little bit more computer science-y, then give it a go. It's kind of interesting, but for most intents and purposes and folks taking this class, don't worry about it. It's a good enough answer, I think. Okay. When creating a new object from outputs of piped functions, place the assignment operator at the beginning. Okay, so we want to create the object, assign it, and then have the data, and then do all of our calculations afterward. No matter how long your chain of functions will be, the assignment will always be done at the top. And I really like this. This is actually just a convention. You can, if you'd like, do the assignment operation at the bottom and have it face to the right. But I like the convention because I think it asks of the user, like, why don't you make a really good object name? And then all of the ingredients of what you're going to make is going to line up with that, rather than I did a bunch of instructions and down here we have this nice little neat thing at the end. Recall last week, we used the filter command to subset data like this. We could make, for instance, this Canada object from the gapminder data, and then just filter to country where values are the same thing as Canada. You might be very familiar with this if you use Excel. That was also called filter in Excel. From here on, for a good bit of the rest of the course, or the rest of class today, I'm going to be describing a bunch of different dplyr functions that are really useful. I don't expect you to like be able to tell me what they all do at the end. Part of the, oh, we have a question. Are these some examples of other commands like lm, which may be, which may need the data to be equals dot? I'm trying to think of like a very common example for which we might have something that's not just data that we would have as the first argument. I'd say that it's not terribly common. But that is just like the thing you would like to do in the case, but it is very uncommon. Of course. Okay. So let's revisit the percent in percent operator. Its common use case that we might want to include in a dplyr operation is for filtering things in some set. So we can use percent in percent, like the equals equals, remember our logical expressions from last week, but for matching any element in a vector on the right. So here we can make a vector. We'll call it former Yugoslavia, and we'll assign it countries that are in former Yugoslavia. And then we can assign to the Yugoslavia object the gapminder data, and then filter country percent in percent our former Yugoslavia vector. And we can now look using the slice operation, the slice function, that the only things that are in our country column are things from our former Yugoslavia vector, but it can match multiple countries and values rather than just one at a time. The slice function is really useful. I use it for this example, but I don't know if there's a slide on it. I don't think there is. The slice function works like head or tail, but it allows you to take rows that are anywhere in your data set and you can index them by number. So you could say like slice, give me just like the middle 100 rows of my data set if I'd like. And so here I've taken just rows 12, 13, and 14. Yes.
Why there is a percent in percent?
Why is the in purple here? That's because of the way that I've made these slides. So in is actually like a special word in R. So like if we go here and we said like in with a capital IN, it would just be like this. But if it's in lowercase, it'll turn colors. That's because it has like a special purpose. And the way that I make the slides means that it's not sure that this is a percent in percent. It thinks it's percent, the special case of in and then percent. That's just a mistake on my part for not making this all the same color. Question.
If we wanted all the countries that were not part of former Yugoslavia, how would you do that with in?
Okay, so there actually is not a reverse of this. The thing that I do is I would say percent not percent or percent no percent, and then I would make my own function that does this. And so it will give me the reverse. That's kind of like the only answer that I have for that. Yeah, is write your own function for it. But another question.
Are surrounded by the percentage side
things beside by the percentage signs, macros. They are operators. So the percent and like the pipe are both just trying to tell you that these are functions that take arguments on either side of them. But I can't think of, there's another one that's percent, $% that I think allows you to take data and then unnest it for formulas. But there are very few cases where percent then something and then percent are like especially supposed to be a special case of a thing. I'm not sure that percent is something related to the magreader pipe for how they wrote it. Okay, let's move on. Distinct is a function that allows you to see the unique values in your data for combinations of columns. So we can say, take the gapminder data and then distinct continent year, and we'll get all of the unique values for the combination of those two columns and the values therein. One thing to note is that distinct drops unused variables. The default behavior of distinct is to drop all unspecified columns. If you want to get the distinct rows by certain values without dropping the others, use distinct and set the dot keep underscore all equal to true. Sorry, we have a question in the chat. Is unique similar to distinct? It is. Unique is the base R version of distinct. Distinct is like in the dplyr package. Unique will convert the thing that you send to it, I think, into a vector. So sometimes you don't want to do that in order to keep the data frame aspect of your data. So we can use distinct and the dot keep underscore all argument set to true in order to keep all of the other columns that were not the ones you wanted to get the unique pairings of or unique combinations of. One thing to note in this example is one of the issues with doing that. Sometimes you will want to do that, but other times it will perhaps throw you off. Let me see, where are we? Okay. So actually, I'll just send this to example. Okay, and if we look at this, we'll see that we have the unique pairings of continents and years, but all of the rest of our columns are now a little bit nonsensical in this case, because now we just have all of the other information for Afghanistan, Albania, Algeria, Argentina, and Australia. And it's very rarely the case that we want to like compare those 6 countries. Maybe at the Olympics or something, but you know what I mean? So I would say be careful if you're going to say to yourself, oh, I'll use the distinct function in order to deduplicate my data. Because sometimes you'll get stuck with nonsensical other information or the information that would be highly specific for which you would like to do your operations. So I would just say be aware of this quality of it, that it just takes the first pairings of all the combinations or the first combinations. Let's talk about sampling rows. We can also filter things at random to work with a smaller data set using the slice underscore sample function. Slice sample is relatively new and is replacing sample n and sample frac and a bunch of other sample underscore whatevers. One thing we could do is like take that Yugoslavia data and then slice sample n equals 6, replace equals false. And now it's just going to sample 6 rows from the data and create a data frame that's those sampled rows. So here we have Serbia in 92, Serbia in 2007, Bosnia and Herzegovina in 2007, Slovenia in 67, et cetera, et cetera. If you want to, at home, sample like this and get these exact same values, you can set .seed 789. And this makes drawing random things repeatable and reproducible. So if you'd like to understand what's going on to make something that's being drawn at random reproducible, you can read the details in the set.seed, but it's kind of wild. I think that it's the math and construction of that under making randomness reproducible is too much for my brain, but maybe you'll have fun doing that. Slice underscore sample can do things other than just take 6 rows at random. You can check the help function for it. Because one thing that I do pretty frequently is sample based on the probability of things or by weights in my data. And slice.sample allows you to do that. So you can, instead of providing an argument to n, provide an argument to prop for like the proportion of the data you'd like to have sampled or something like that. You can also, let's say you were working with, I don't know, the longitudinal employment household data, and you can use their sampling weights in order to weight the random draws so that it's a pretty decent approximation of your whole data set, for instance. Question?
Do you know if you can do like a stratified sample? So if you like, I want 10 from Asia, 10 from Europe.
Yes. So we're going to be discussing what function does that in a second, but you would use a group by function to group by your countries, and then you would sample n equals 10, and it would give you 1 or 10 for each of your groups. Yes.
Is there any rationale for giving that number 789?
Can you say one more time?
I'm just asking, is there a reason for selecting that number inside the
Oh yeah, there's no reason. I just like this why is 6 afraid of 7 joke, so that's why I picked this one. But often people just like pick something that is going to be something that their team will remember or something of that kind. A lot of people will just pick one so that it's really easy for everyone to just use it when they try to run their data again for something like that. So the number is just to say this is the random draws that we're going to use. Okay. Of course. One thing you might want to be interested in doing is sorting your rows. Maybe you just want to make a Pander table that is sorted in a meaningful way and not just randomly how the data was created. You can use the arrange function to do this. So we can take the Yugoslavia data and then arrange by year, and then within year, descending population. And so now our resulting data frame will be 1952, then 1957, and so on for ascending year. And then it'll also, within each year, do descending population. And the really cool thing about arrange is it also arranges characters. You can have it do things alphabetically and do things numerically. It's like willing to do that. Yeah. Often it's the case that we want to pare down our data set to just some set of columns for which we're extremely interested. So not only can we limit those rows, we can also include specific columns and put them in the order listed using the select function. So here I've taken the Yugoslavia data and then selected country, year, and population, and then taken the first 4 rows of this. And now the only columns in the data set are the ones that I've selected here. An interesting thing to note here is that I didn't have to put country, year, and population in quotes. You can just kind of name the variables in your data in the select function, and it will be happy to take care of that. We'll get into a little bit, we'll get into an explanation of why you don't need to use quotes, even though if you're used to base R or something or data.table, you're probably very used to putting things in quotes. We'll be discussing that, I think, might be next week. I don't remember. You can also drop columns using select. So instead of picking the specific ones you want to keep, you can specify the ones you want to get rid of. You can do this using the subtraction symbol. So we can take the Yugoslavia data and then select minus continent, minus pop, and minus life EXP. And then we're left with country, year, and GDP per capita. Neat. There's a lot of really excellent helper functions for select. There are things like starts with, ends with, and contains, or it can be given a range of contiguous columns. So you could say like, just give me columns 1 through 5, and it will give you the first 5 columns left to right. But I want to motivate the use of these other helper functions, like starts with and ends with. Here I have like a screenshot of the Denver Youth Survey. And here is some information about at what age people get married. These helper functions are particularly useful when you have wide data frames like this, where one person is answering one question, but that question is turned into a column for each of the possible responses. So here we have, was somebody married at 10, married at 11, through married at 25 or 26, I believe. Yeah. So you could just take the Denver Youth Survey and then select starts with the word married, and it would give you just the columns that start with the word married. Or you could say, take the Denver Youth Survey and then select ends with the number 18, so that we're looking at just the 18-year-olds in the data set, and it'll give you this. This is like tremendously useful, particularly with survey data that's often in this format. Question?
I have another little thing. Have you heard of everything?
Yes, everything is really great.
Yeah, I was just gonna bump that.
Yeah. If you are watching this later, do the question mark everything, and you can check that out. Okay. What's ends with used for? Okay, so you can use ends with for like, I'm trying to think of an example from some data. So I've used like the American Community Survey quite a lot. If you want to get the replicate weights from that, you could say ends with WT, and it would give you all of the replicate weight columns. Whereas, yeah, cool. Another helper function that's I like use a ton, like I can't plug this helper function enough, is where. It can be used for selecting columns based on functions that check column types. Okay, so we could say, take the gapminder data and then select where is.numeric, and then give me the first 3 rows of that. And it will only keep columns that are numeric in how their the values are. You can also say things like in the gapminder data, select where is.factor, and it'll give us like the country and continent columns. While slightly beyond the scope of this class, I always try to let you know of like the broader things that could also happen. You can just supply this a function. So sometimes you can write your own function there. So you can say select where is, or select where, and then write your own function there. And this is very useful as you get into like more advanced R. So there's one more thing I wanted to say on this slide. Okay, so is.numeric and is.factor are functions, but note that we're not using their like parentheses like we typically do when we use functions thus far. This is will be described more thoroughly in week 7. But what's happening here is it's treating things as if it's applying them. So it's like vectorizing these functions. We'll get to more into what that means later, but that's why we don't have to put parentheses here. It's going to be okay. We can rename columns using select. This will drop everything that's not mentioned though. So we can say, take the Yugoslavia data and then select, and then our new name will go first, and it's going to be equal to the old name. So we'll say life underscore expectancy is equal to life exp, and then we'll take the first 4 rows of this, and note that there's no other columns here. It's just the one for which we've renamed it, and it's called life expectancy now. If you were going to change something after this head 4 here, you could not call the life exp column. That one's gone now. It's called life expectancy. This is a little bit dangerous. One thing I would recommend instead is to use the rename function. Rename does what it sounds like. It renames variables using the same syntax as select, but it does not drop unmentioned variables. And so typically what we want to do is like keep all the data that we may possibly use up until the point we don't need them anymore. And rename allows us to do this. So here we take the Yugoslavia data, select country, year, and life expectancy, and then rename the life expectancy column using the new name equals the old name syntax, and then take the first 4 rows and we get our country, year, and life expectancy with the new name columns. I want to talk a little bit about column naming practices. Good column names will be self-describing. Don't use inscrutable abbreviations to save typing. RStudio's auto-completing function takes away the pain of long variable names, so you can just hit tab while writing code to autocomplete. So you don't have to just do, ASDF1, ASDF2. Valid naked column names can contain upper or lowercase letters, numbers, periods, and underscores. They must start with a letter or period and may not be a special reserved word. So earlier we talked about like in is a special reserved word. True is a special reserved word. If, for, else, while. Names are also case sensitive. So year with a capital Y and year with a lowercase y are not the same thing. You can include spaces or reserved words if you put backticks around the name. Again, backticks is the button just below the escape key. Spaces can be worth including when preparing data for your ggplot or your pander, since you don't have to rename the axes or table headings. So a lot of times what my code will look like is some data set. I do a bunch of manipulations and adding columns and getting rid of columns and what have you. Then I do a rename where I put spaces in between life and expectancy or that kind of thing, and then pipe that into a ggplot so that things look nice right at the end. So I tend to do the things that make things look really nice like adding spaces right at the moment of this needs to look nice. Whereas if I have it up at the top, sometimes that makes it more difficult for the tab autocomplete to pick it up, and also can make names less clear when I come back to the code. An example, so I'll load the Pander library, we'll take the Yugoslavia data and then filter just to Serbia, and then select year and life expectancy, and then rename them year with a capital Y and life expectancy with a space. And note they're between backticks. Again, that's the key above tab and below escape. And then take the first 5 rows and then throw it in a Pander. And so now we have this nice little life expectancy title instead of life exp or life expectancy with a dot or an underscore in between. You can create new columns using the mutate function. Why it's called mutate is like a 80s computer nerd reason. We don't have to get into that, but mutate creates new columns. For instance, we can take the Yugoslavia data and then filter country equals Serbia, and then select the year, pop, and life exp columns, and then mutate pop million is equal to pop divided by 1 followed by 6 zeros, and life exp past 40 equals life exp minus 40. And then we look at the first 5 rows and we see that our new columns are here, and they're in the order that they were created from left to right. One thing to note is that in order to make multiple columns in the same call, you can just name this, then what operation you want to do with those columns, and then a comma, and now you can make a second column. You can also, this is the moment that the column gets made, so you can actually use that again. I'll give you an example. Actually, might have to make the Yugoslavia data real quick. Okay. So let's say that we wanted to take the Yugoslavia data and then filter to Serbia, and then select year, pop, and life exp, and then mutate pop million. But then we also want pop 1000. We can take pop million right here and divide it by 1000. That's how that works, right? Multiply by 1000. I don't remember. I'm not great at math, but so even within the same mutate call, you can call something that you've made. So like I've taken this and it's also right here. This is often useful when you have like one particular thing you want to do with a column in an if else statement, and then you need to change the column for all other qualities after that. I often find myself like changing NAs to zeros, and then in the next thing, taking the mean, right? Something like this. Okay. Let's talk about if else. If else, the function, so there's if else the operation, we'll get into that later, but this is if else the function. It's a common function used within mutate and in general R programming. It returns a vector of values depending on a logical test. So these are the same kinds of logical expressions we were talking about with filter. The syntax of it is, it'll be like if else, the test, and then to test equals, we'll provide the argument of whatever logical expression we're interested in. And then when this is going to be true, when this is a yes, do the first value, and when it's a no, do the second value. Okay. The output from an if else function call is going to be true, false, or NA. Note that you can't test for NA with inequality. Okay, so you can't say like, is 33 an NA? That's not how a logical expression works. We'll talk about what to do in a second for that. So for example, we can make a vector with the elements 1, 0, NA, and -2. And then in the if else function, we'll say the test is example greater than 0? If it is, then it's a positive number. If it's not, then it's not positive. Okay. And when we run this, 1 is greater than 0, so we get a positive. 0 is not greater than 0, so it's not positive. NA cannot be tested with an equality, so it just throws us back in NA. And -2 is not greater than 0, so we get a not positive. Does that make sense? Let's talk about how we're going to use that within a mutate call. We can take the Yugoslavia data and then mutate a new column called short country, which is going to be equal to, if else, country equals Bosnia and Herzegovina, return B and H. If not, return as dot character the country column. And then select country, short country, year, population, and then arrange it by year in short country. Okay. So here's how we're going to read this. For each row, if country equals Bosnia and Herzegovina, make short country equal to B and H. Otherwise, make it equal to that row's value of country. This is a really simple way that we're able to change some values and not others. So here, when country is equal to Bosnia and Herzegovina, we got B and H in the short country column, but everything else just gave us back that same value in their country column as a character. Note that since the country column in the original Gapminder data is factors, I had to convert it into a character in order for this to make sense. That's neither here nor there. Also, before I forget, if else is a base R function. There is a if underscore else that I believe is in the dplyr package. It might be in the tidier package. It does basically the same thing, the if underscore else one, but it has some stricter rules about how it coerces things into other values. I'm like not explaining that right now, so because that's kind of what we're going to go over next week. But if you do encounter if underscore else, know it's doing this, but it's a little bit stricter on the rules. Okay. Recode is another base R function that's useful inside of mutate calls. We use recode to change specific values to other values. This is particularly true of factors. So you can change multiple values at the same time. Note that if a value has spaces in it, you'll have to put it in backticks in order for recode to understand what you mean. So for instance, we can say, take the Yugoslavia data and then mutate country equals the recode of country, where Bosnia and Herzegovina is going to be equal to B and H, and Montenegro is going to be equal to M. And then give me the distinct values in the country column, and we'll see that it has changed our factors names to B and H for Bosnia and Herzegovina and M for Montenegro. Cool. I tend to use case when quite a lot. Case when performs multiple if else operations at the same time. I believe it's the same. It might be the same as gen replace in Stata. I don't know. It's been some time since I was using Stata. Case when allows you to create a new variable with values based on multiple logical statements. This is useful for making categorical variables or variables from combinations of other variables. For instance, we can take the gapminder data and then mutate a new column called GDP per cap ordinal. And this is going to be equal to the case when GDP per capita is less than 700, return low. If GDP per capita is greater than or equal to 700 and GDP per capita is less than 800, return moderate. And then true, return high. And so this means all other values return some value. So things that are not satisfying either of these conditions will return high. And then we can slice just to get rows 6 through 9 to see what happens. And for Afghanistan in 1977, we have a moderate level, which is at 786. So we'd expect it to be between 700 and 800. When it was 978, it was high. And when it was 649, it was low. Question?
Put the output as numeric, or do you have to do it as?
You can put the output as numeric. You would just not put these things in quotes and for whatever numbers. Another question. Could you explain recode again? Sure. So recode allows us to change the specific values of things, particularly that are factors. Okay, so here I changed the country column to recode the country column. So whenever it says Bosnia and Herzegovina, now it says B and H. And whenever it says Montenegro, now it says M. But it keeps all of the other qualities of that column. So it's still a factor, and it still has the underlying numbers that allow it to be a factor. So it's just like a quick way to like change the human legible part of the factor variables. We are going to be covering the tidyverse way to recode factors later on in this course using a package called 4cats. So if you don't have like a really prescient reason you would need to use recode right now, I'd say don't worry about it so much. Does that help? Okay. Let's talk about poll. Sometimes you want to extract just a single column from your data frame as a vector or as a single value. So poll will pull a column of a data frame out as a vector. So we can take the gapminder data and then pull life expectancy and look at the first 4 elements of it. And we'll see that it has this vector syntax in the output. So instead of it saying a tibble with however many columns and rows, it's just one, I'm forgetting the jargon there, for each of these 4 elements. Whereas if we said gapminder and then select life expectancy and give me the first 4 rows, it'll keep the data frame formatting of it. So I often use poll when I want to put like an inline piece of information in my markdown. right? Like if I want to just like give me this one column, I'm going to take the mean of it. And then my sentence is, this is the mean of such and such column. That's often when I would use pull. You'll note that if you tried to use mean on after a select call, it would yell at you. Okay. Here's an example. So pull is particularly useful when you want to use a vector-only command in a dplyr chain. So this is some inline code. The average life expectancy in Afghanistan from 1952 to 2007 was backtick R, gapminder data, and then filter country equals Afghanistan, and then pull the life expectancy column, and then take the mean, and then round it to 1 decimal place. Backtick years, and it will produce this sentence. So mean can only take a vector input, not a data frame. So this won't work on select instead of pull. Next, we're going to get into summarizing. I think we should take a 5-minute break, and then we'll come back. Okay, great. I think it's been 5 minutes. My tea got cold, so it's been at least some time. Let's get back into it by talking about summarizing with dplyr. Actually, before that, do we have any questions? Yes, a hand in the class.
I noticed the code from last week's lecture when you were slicing particular subsets of data to use. So say data for a particular continent. When you were doing that, you were including the head, comma 4 code.
Mhm.
What purpose does that have when you're making a plot? That question makes sense. I guess what would it do if you create that subset of data and then you make a plot with it? How does that function in that context?
Okay, sure. So head just only returns the first n amount of rows in your data frame. So if I were going to make a scatter plot, and let's say my original data set at 100, and then I use the head function, it will only get rid of, or it will get rid of all of the 94 rows underneath the first 6. And then I would have a scatter plot with 6 points on. Cool. Do we have any other questions? Great. So summarizing with dplyr. So for general aggregation, we use the summarize function. Note that Hadley Wickham, I think, is from New Zealand. So you can actually use summarize with an S. You'll see that in a lot of code, summarize with an S instead of summarize with a Z. I'm from the US. I think summarize has a Z in it. Both of them work. You'll also note in ggplot, color with a U also works for the same reason. But summarize takes your columns of data and computes something using every row. Okay, so you can count how many rows there are, or calculate the mean, or compute a sum, or obtain a maximum or minimum value. You can use any function in summarize that aggregates multiple values into a single value. Like the standard deviation function, the arithmetic mean function, or the max function. Yeah. An example. So let's say for the year 1982, we want to get the number of observations, the total population that year, the mean life expectancy, and the range of life expectancy for former Yugoslavian countries. So we can take the Yugoslavia data and then filter so that year is equal to 1982, and then summarize, and we'll make this new column, n obs is equal to this n function. This will just count things. Total pop is equal to the sum of the population column. Mean life expectancy is equal to mean life exp, and range life expectancy equals max life expectancy minus min life expectancy. And it will return to us a data frame with each of these 4 columns that have been created by these functions. So it's like a mutate call, but instead of it creating a new column, it is aggregating new columns. And so what you have returned is a table with 1 row, the number of observations, 5, the total population, 2 million, 20 million, mean life expectancy, 71.3, and the range life expectancy, 3.94. So these new variables are calculated using all of the rows in our Yugoslavia data in 1982. We may want to avoid repetition using summarize. I think that's one of its strengths, is that I don't have to like keep writing out Yugoslavia and then pull and then mean, something like this, for each of the operations I'd like to do. But one way to make that yet faster is to use the across helper function. Maybe you need to calculate the mean and standard deviation of a bunch of columns. With across, you can put the variables to compute using either the vector concatenate function or select syntax, and put the functions to use in a list afterward. So here we take the Yugoslavia data and then filter to 1982, and then say, summarize across our life expectancy and pop columns, and then list will get the average, which is equal to the mean of dot, right? Because we're going to be giving that information to the dot, and SD is going to be equal to the standard deviation. And what we'll receive back, it will return life exp underscore AVG. AVG is coming from here to give us the life expectancy average, as well as the life expectancy standard deviation of 1.6, which is this operation is being run over here. And it does the same thing again for our population column. So we can get our pop average here and our pop standard deviation here. Note it automatically names the summarized variables based on the names given to list, which is just wild to me. Every time it happens, I'm like, so quick, so easy. When I was first learning R, the way that you do this was a lot more complicated than this, but it's still, once this came out, I was still like too novice to be using this. I would say that like don't feel some type of way about if this is like a lot of stuff going on. An operation like this isn't something I picked up in my own R use until just a couple of years ago. One thing that might happen when you're doing a lot of summarizing across several columns is you'll get the sense that there's way too many parentheses going on. What happened to the legibility of dplyr, you might say? It can get hard to read code when there's lots of nested functions like this. Break up things when they get confusing. So this might be a time to use return so that you can say, okay, we filter the data and then we're going to summarize across these 2 columns. And then within our list, we run these 2 operations and then let all of our ending parentheses kind of hang. One other thing that you might want to do that I also do is use rainbow parentheses. I couldn't make them like go to the slides, part of the way that I make the slides, but I have it set on this computer here, so you might be able to see an example here. So like the each part of the nesting is colored the same way. And also when I click on it, tells me where the other one is. So it's like, here's the orange one here, but it'll highlight where the other one is, that kind of thing. At least to help you get your bearings. How do you turn that on? The rainbow. Oh, yeah, I probably should have said that instead of just being like, look at this awesome thing. You go to, my bad, I didn't even explain it when I went. You go to Tools, Global Options, and I believe it's under Code, Display, and then down here, rainbow parentheses. So you can toggle that on and hit OK. And rainbow parentheses. Yeah, I'm sorry I couldn't put them in the slides. Part of it is that I have to write a CSS code to help manage what all happens in the slides, and making the CSS code read when things are nested and then paint them different. That's way harder CSS than I know. So another way we can avoid repetition is to use across for other repetitive operations. So we could say across everything, big shouts. We can say across everything, which will summarize and mutate all variables sent to it in the same way. For instance, getting the mean and standard deviation of an entire data frame. So you could say, take this data frame and then summarize across everything, and then take the mean and standard deviation of that within a list. Note that it'll kick back an error if you have like a character variable in there or something. But if you have all numbers, then it will just go. You can also say across where and nest a where helper function inside of across, and it will summarize and mutate all variables that satisfy some logical condition. For instance, summarizing every numeric column in a data frame at once. So then you don't run into the issue of like, what if there's a character vector or a character column here? You could summarize across where is dot numeric, and then run your mean and standard deviations that way. One thing I tend to do is mutate across my whole data frame for making things lowercase. I'll give you an example of this. So we could take, I'm trying to think what's the data that we have that we know. We can take the gapminder data and then mutate across is dot factor, and then say something like function x type as dot character string to lower dot. I wrote this in the old way, but it still works. My bad. But something like that. I wish I had a better example where they already came out as characters, but if you ever run into that issue, just let me know. I'll send you code that is not using data from the class. Anyways. One important thing we'd like to do when we summarize things is to look at different categories and groups. We can use the group by function in order to do this. If you're familiar with SQL, I'm sure this is very familiar to you, but the special function group by changes how functions operate on the data. It's especially important for summarize. So functions after group by are computed within each group. I'm going to say that again because it's really important. Functions after group by are computed within each group as defined by variables given, rather than over all rows at once. Typically, the variables you group by will be integers, factors, or characters, and not continuous real values. So you're more likely to group things into countries and not their life expectancies, right? This is the analog for this in Excel are pivot tables. An example might be, we can take the Yugoslavia data and then group by the year. So now we're going to be binning things by their years, and then summarize the number of countries by n distinct countries. The total population is going to be the sum of the population. The total GDP per capita is going to be equal to the sum of population times GDP per capita divided by the total population. Note that total pop is made here and then used here. And then we get the first 4 rows of this. And now what our data frame looks like for each year, so it's grouped by these years, we can get the number of countries, the total population, and the GDP per capita for all of the countries in each year. So because we did group by with year, and then we summarized, we get 1 row per value of year. It's really neat. Sometimes you'll do a group by and then a mutate, and your data frame will still be grouped once you're done. So one thing you might want to know is how to ungroup things afterward. It's just the ungroup function. So you can add that at the end of the chain to make sure that your data is back to just being everything can get manipulated at the same time. I don't think that's going to come up for your homework until I think group or homework 5. So you'll see another example of what I'm saying out loud. Anyways, one thing you might want to check out are window functions. Grouping can also be used with mutate or filter to give rank orders within a group, to make lagged values of some data or cumulative sums. You can read more about window functions in the vignette that I've linked here, which I'm not sure I checked on this link. I hope it's still here. Okay, great. So for instance, you can take the Yugoslavia data and then select country, year, and population, and then filter year is greater than or equal to 2002, and then group by the country, and then mutate. The lag population is equal to the lag function of the population, and then ordered by year. So it knows that within each country group to check the previous year for that population number. And then you can make population change column is equal to the population minus the lag population that you made here. And when we look at this, we'll see that for Bosnia and Herzegovina in 2002, population was this. The lag population is going to be an NA because there isn't a earlier year in the data set than 2002. But for 2007, the lag population is the same as population here. And the same thing for Croatia. The lag population in 2007 is the same as the population was in 2002. Okay, now we're going to talk about joining and merging data frames. When do we need to join tables together? When we want to make columns using criteria that's too complicated for if else or case when, it's typically a good time to join tables together. That means we can work with small sets of variables and then combine them back together. You may want to combine data stored in separate data sets. So something like local lockdown measures and stationary bike sales. Like these are going to be 2 disparate data sets, but they're linked together conceptually for us. And so we would want to join them together to understand some information, right? Often large surveys are broken into different data sets for each level, something like household, individual, neighborhood, and so on and so forth. And for this, we would need to join tables together. So let's talk about what the concept is of joining. We need to think about the following whenever we want to merge data frames. And we're going to call these data frames A and data frame B. The first question we want to ask, which rows are we keeping from each data frame? Okay. Then we want to ask, which columns are we keeping from each data frame? And then we want to ask, which variables determine whether rows match? okay? So we want to know what rows we're keeping, then what columns we're keeping, and then what can we use to match them together. So this slide has a lot. I'm about to say many words. One thing I want to tell you now is that typically you just need a left join or an inner join. The other ones I will describe though. So there are tons of joins. As I said, usually left join does the job. And left join is saying you want to keep all the rows from data frame A. Wherever they're matched with data frame B, wherever possible, and then keep columns from both data frames. Okay? And I like the logic of this, where I have like my main data set and I just want to like append it with something else whenever that something else matches my main data set. Okay? So often what this looks like for me in my data, so I have this project I was working on that was about union elections in different states. And I wanted to get some information about like manufacturing employment in those states. And so I was going to join data to my union elections data. They're in different states, but my manufacturing data also included like DC and Puerto Rico and Guam and Samoa, okay? But my elections data does not have those. So like when I joined it together, it's gonna drop DC and Guam and Puerto Rico and Samoa because it's not matching like my main data set. So that's kind of the logic of the left join is like, I have one data set that's like my main bag. And then when I join something to it, it's gonna drop the stuff from the B that doesn't matter and doesn't match. And it's gonna keep the columns from both, okay? Here's what the syntax will look like for this kind of join. You'll have your data frame A, and then you'll left join data frame B to A, okay? A right join is just the opposite of this. We keep all the rows from B, match with A wherever possible, provide an NA when not, and keep columns from A and B. So for this instance, it's just the directionality of it. It'd be like if I took my elections data and then attached it to the like manufacturing employment data, but it would still provide me NAs for those other things. But the directionality is just conceptual as the difference between left and right joins. Inner join keeps only rows from A and B that match and keeps columns from both A and B. Okay, so an inner join is not going to provide you NAs where things do not match. Okay, so it will just drop rows. Often an inner join will get rid of rows. Whereas like a left join, you'll probably keep the same amount of rows, but get more NAs in some columns. A full join keeps all rows from A and B, match wherever possible, and makes an NA for all the things that don't match, and it keeps all of the columns from A and B. So this one just says everything gets slapped together, and if it doesn't match, it's all NAs, don't worry about it. I do not use full join very often for the same reason. Like I don't need to keep all of these extra NAs typically for the kinds of joins I do in my work. A semi-join keeps the rows from A that match rows in B and keeps only the columns from A. Okay. Semi-join is often useful when you're like looking for a specific thing that's maybe not in your B data set or that is in your B data set, but you don't want to attach all the columns. So I find semi-join I only use when I want to check what kinds of matches I have in my B data set, but my B data set might be like huge. And so I don't want to join all those things. I have a slide a little bit later about why that is. And the last one is anti-join. Anti-join will keep rows from A that do not match a row in B, and keeps columns from only A. So this is an example of like, sometimes you want to manipulate some data. So you'll take out part of your big data frame, manipulate it, and then use it to filter things. So anti-join's really good for getting rid of some particular use cases for which an if else or like a case when is like way too complicated to do. Okay. Let's talk about matching criteria when it comes to joining things. We say rows should match because they have some columns containing the same value. We list these in the by equals argument of the join. So the matching behavior, if we don't add anything to the by argument of our joins, it will match using all variables in data frame A and data frame B that have identical names. Okay, so like if we have two data sets and both of them have a column that's called year, and we just say left join them together, and we don't say by what, it'll be like, oh, well, they both have year, so that must be what they mean. Okay. Another thing we can do is say by equals, and then some set of variables. And these are variables that have the same name in both the data sets. So we can say var1 and var2 and var3, and it assumes that var3 is a name of a column that exists in data frame A and data frame B. If it does not exist in both of those, it'll yell at you. If it does, it'll match based on those characteristics. And lastly, what we can do is say by equals, and we can say a variable from data frame 1 is equal to a variable from data frame B that has a different name. So like sometimes in my data, it will say something like, this is going to be state name, and this one will be state all caps. But I don't want to take the time to change all the names of them because I'm just joining this really quick, no big deal. And then we can also say, like add more potential pairs that are named two different things by using a comma and also using this equals syntax. This will match identical values of data frame A variable 1 in A to B var 1 in data frame B, and so on. Note, if there are multiple matches, you'll get one row for each possible combination. Okay, so I'm going to say that again. If there are multiple matches, you'll get one row for each possible combination. So let's say we were matching to like that Bosnian or Bosnia, the Yugoslavia data, and we're matching some information about Montenegro, but the thing that we're matching to it has like Montenegro for like 1952 6 times. That means that it'll join and it'll make 6 columns for each of, or 6 rows for each of those matches that it did, even though to us we're like, that's just duplicates, who cares about that? Okay. This will often be a source of R crashing if you have way too many matches of that kind, because you could very quickly make 2 data sets that have 1 million rows become 1 data set with 1 billion rows. You see what I'm saying? Okay. If things need to get more complicated than like 1 left join or like 1 semi join or 2 left joins, break it out into more and more operations. That brings us to our data that we're going to be using for the homework this week, the NYC Flights 13 data. We'll use data from the NYC Flights 13 package to install it and load it. You can run it like this. It includes 5 data frames in it. Okay, so like the Gapminder data had 1 data frame in it. But now we're going to be working with 5 different data frames, and they can all be joined together through different ways. So one of the great things is that it has a bunch of different possible joins you can be doing. Here's a little bit of a description of what happens. So it has 5 data frames, some of which contain missing data that'll be coded as an NA. It has the flights data, which are flights that are leaving JFK, LaGuardia, and Newark. That's the other one. I'm from Atlanta. I don't know nothing about airports. Yeah, everybody comes to Atlanta. What else is there to know? We have the airlines data, which are going to be like airline abbreviations. ASA for Alaska Airlines, stuff like that. We have airports metadata, so specific data about where all of these planes are landing. We have information about the planes. So this is like things like how big are their engines and stuff like that. And then we also have hourly weather data from each of these departure places. So JFK, LaGuardia, and Newark. Note that these are all separate data frames. And so you'll have to load them like this. You could say data flights, data airlines after you've loaded the library. Okay. So let's talk a little bit of the examples of what you could join together. So here we can take the flights data and then filter the destination to Seattle. And then we can select the tail number from the flight and then left join the planes data and then select from the planes data just the tail number and the manufacturer and then join it by the tail number. And then we can count how many manufacturers were involved in flights that left anywhere in New York or those 3 New York places in 2013 and landed in Seattle. And then we can arrange them in descending order. And we'll get a table like this. It'll say Boeing made 2,000 of those planes, Airbus made 475, et cetera, et cetera. Note you can perform operations on the data inside the function of a left join, and the output will be used in the function. So here, like I took the planes data and I manipulated it right in here, just so I could append just the manufacturer column to the rest of this information. A slightly more complicated example. Which airlines had the most flights to Seattle from New York City? We could say, take the flights data and then filter that the destination is Seattle, and then select the carrier, and then left join the airlines data by carrier, and then group by the name of the carrier, and then tally. So tally is a shortcut for summarizing the number of observations. So earlier I said like summarize n obs equals n function, right? Tally lets you do that in one line instead of having to type more. It creates a variable called n. So does count. So that's what was happening here. Count also makes a variable called n. So that's why I was able to arrange a descending order of n. So that's what this is. But here we can see that the most flights to Seattle from New York City were Delta, big shout out to Atlanta, and United Airlines, and then Alaska. Another joint example is the relationship between departure delays and wind gusts. So first, I'm going to load the ggplot2 package so we can make sense of this. We'll take the flights data and then select the origin, the year, the month, the day, the hour, the departure delay of these flights. And then interjoin the weather data by the origin, year, the month, the day, the hour. So we need to interjoin here because all of the other information is superfluous to our understanding of the weather and departure delays. So we only want to keep the things that match because we don't care about the weather elsewhere. And we don't want to keep those NAs. And then we're going to select just the departure delay and the wind gusts. And then, and this line's cool, and you'll probably be using this a lot moving forward, is filter to get rid of NAs. So in order, you'll recall I was like, you can't use a logical expression to deal with NAs. There's actually a function for this. It's called is.na. And one of the ways that people tend to get around and drop rows that are NAs is to say is.na, the column. And this will get rid of the NAs that are in this column. And then we also say and is.na wind gusts. And so this column or this line will filter out all of your NAs. And then we'll pipe it straight to a ggplot with the aesthetics, mapping the wind gusts to the x-axis and departure delays to the y-axis. We'll make it a scatter plot and put a smoother through it. Also, because data are the first argument in ggplot, we can pipe them straight into a plot. This is often how I would do it. In my own work, I don't tend to use the data equals something in ggplot. So check out those 1,200 mile/hour winds over there. They actually, this was what the data was like when I first took this class, and I like to keep it around that it used to have these data points in it that were totally incorrect. So this is me also plugging that sometimes it's really useful to just make quick plots of this kind to help troubleshoot your data and recognize where like things are going wrong. Note that you cannot recreate this plot if you just installed NYC Flights 13. They got rid of this kind of thing. But we can redo this after removing the extreme outliers. At least in the data I have. Again, you won't have to go through this part. But here's a piece of code to look about how you might go about getting rid of that kind of point. And I also got rid of the geom point, so you could just look at the trend. And it seems pretty clear what's going on here. When the wind gusts are really high, departure delays go up. Okay, so some suggestions for tinkering when it comes to your joins and what you'll be working on in your homework. The reason I'm providing these is because I know that some folks see this homework assignment and are like, I don't even know what to ask. So here's the place you could start. What are the names of the most common destination airports? Which airlines fly from New York City to your home city? Is there a relationship between departure delays and precipitation? What is the distribution of departure times for flights leaving NYC over a 24-hour period? Are especially late or early arrival departures to some regions or for some airlines? One warning I have is that the flights data has 336,776 rows. So if you do a sloppy join, you can end up with many observations, many matches per observation, and your data will explode in size and you will crash your machine. This might not be true if you have like a really cool computer, but my laptop is not big enough to support a sloppy join of this kind. So just note that if your computer crashes while you're working on this homework, maybe you need to like go back and check the way that things got joined together. So here's the homework for homework 3. Pick something to look at in the NYC Flights 13 data and write up a markdown file showing your investigation. Upload the markdown and the HTML to Canvas. You must use at least once a mutate, so that's making one new column, a summarize, which is aggregating all of the rows of a column, a group by, which is like putting things in bins based on some sort of conceptually interesting value in your data, and any join. Left join, anti-join, semi-join, do what you got to do. Include at least one nicely formatted plot and one table. In plots and tables, use nice variable names. So maybe try out spaces, put them in backticks, and make sure that things are rounded to 3 digits or less. This time include all of your code in your output document. So say echo equals true, so that people can follow what all happened and then see what returned. Be sure to also use comments. Remember, after a hashtag, you can hit space and then write a comment about what's going on within your code, and line breaks to separate commands so that things aren't all on the same line, so that it's clear to a peer what you're doing or trying to do. You must write up your observation briefly in words as well. Note, if you want to see the NYC Flights 13 data frames in the environment, you'll need to load each one. You could say data airlines, data airports, data flights, data planes, data weather, for example. I feel like there was one other thing I wanted to mention before this. Just as a reminder that if something is taking you longer than like 5 to 7 minutes, like reach out to somebody. Maybe me, maybe the Slack, maybe the class mailing list. The homeworks are going to become more time consuming here for the next few homeworks. I think this one, depending on your like comfort with joins, could be time consuming. So please, if something is taking longer than 5 minutes, not joking you, like one length of a song, reach out. Do we have any questions? Okay, cool. Well, thank you all so much. Have a good weekend.